Hello, I am Karen Fox with NASA's Office of Communications, and we are here today at the Johns Hopkins University Applied Physics Lab in Laurel, Maryland, to talk about NASA's first test for planetary defense. This is the Double Asteroid Redirection Test mission, which is going to test one way to change an asteroid's movement in space. We're planning to launch in late November. Everybody in the room here today is vaccinated. We are following CDC and APL guidelines for social distancing and for masking. However, speakers will be taking off their masks when they talk. Our speakers are going to be Lindley Johnson, the Planetary Defense Officer at NASA headquarters in Washington, Nancy Chabot, the Coordination Lead on DART here at APL, Elena Adams, the DART Missions Systems Engineer here at APL, and Andy Chang, DART Investigations Team Lead at APL. After they speak, we will open up the phones to Q&A from our media. You can press *1 in order to get into the queue for those questions. And additionally, we will be taking questions from social media at #AskNASA. So with that, let's get started with Lindley Johnson, who is going to tell us about NASA's Planetary Defense Program and how DART fits into that.
Well, thank you, Karen. We in the Planetary Defense Program at NASA are very excited to be at this point in preparing for the DART launch. It's been a few years in development, and we're really looking forward to getting it into space. We in the Planetary Defense Coordination Office at NASA oversee the strategy that we have for planetary defense. And it has several sectors, the first of which, of course, is the most important one, and that's we got to find them first. Our capabilities to search, detect, and track these objects and determine their orbits to see if any of them really are a hazard to the Earth. It's very rare for an asteroid to impact the Earth, but it's something we want to know about well ahead of time. So we're out there searching the skies, developing the catalog of all the asteroids and comets that can come near Earth. The second big portion of our work is then characterizing those objects, determining what their sizes are. Most of them are so small that even if they were to impact the Earth, they would disintegrate in Earth's atmosphere. But others are much larger, like Didimos. Now, we've been tracking and characterizing Didimos and its moon for many years, so we have a good understanding of what this asteroid system is. Then we spend a good deal of effort planning and coordinating with other agencies in the U.S. government and our international collaborators in space agencies around the world on what would be the response if we were to find an object that was on the impact trajectory with the Earth, and planning with them what we might do and who is going to do what as far as response to an impact threat. Then the action then is, of course, mitigating. Hopefully we are able to do that well out into space before the asteroid is any imminent danger of impacting the Earth. And that's what DART is all about, a test of a capability to deflect an asteroid. All of this is part of a national near-Earth object preparedness strategy and a plan that was developed over a course of 4 or 5 years and released in 2018 with these 5 goals that you see here. So goal 3, testing NEO deflection and disruption and mitigation capabilities. That's what DART is all about, our first test of a capability to do this. And so with that, let's hear more about DART.
Fantastic. Thank you, Lindley. Sorry. Next up, we have Nancy, who is going to talk us through the DART mission specifically.
Great. Thank you so much. I wanted to talk a little bit about why these asteroids were chosen for the DART mission. First and foremost, these asteroids are not a threat to the Earth. They are not a danger to the Earth. They are not on a path to hit the Earth in the foreseeable future. That makes them appropriate target for a first test. But what really makes these asteroids ideal for this first test is because it's a double asteroid system, just like the name of the mission says. There's 2 asteroids here. There's Didimos, the larger one. It's 780 meters in diameter, and it has a small moon asteroid that goes around it. It's named Dimorphous. It's 160 meters in diameter. And telescopes on the Earth have been looking at this double asteroid system for decades. Because of the telescopes here on the Earth, we know that this smaller Dimorphos goes around Didimos every 11 hours and 55 minutes, just like clockwork. And we've been watching that for quite a while. So what DART is going to do is it's going to come speeding in really fast, 15,000 miles per hour, and it's going to target onto Dimorphos, the smaller of those 2 asteroids. Now, DART's also carrying LICIACube, which is a CubeSat contributed by the Italian Space Agency. It's kicked off 10 days in advance, and it'll fly by after DART's collision roughly 3 minutes. And it'll take some spectacular images of the ejecta that we'll talk more about later. But now what we've done is the DART spacecraft is totally destroyed. LICIACube is long gone. How are we going to know how much we deflected this asteroid? Well, we're going to use these same telescopes here on Earth that have already been looking at this system for decades, and they're going to turn their gaze back on this asteroid system. So if you think about it, the DART spacecraft, the main body of it is about 100 times smaller than Dimorphos, the asteroid that it's targeting. So you can see this isn't going to destroy the asteroid. It's just going to give it a small nudge. It's actually going to deflect its path around the larger asteroid. So we're demonstrating asteroid deflection in this double asteroid system. And it's actually just a small nudge. It's only going to be a change of about 1% in that orbital period. So what was 11 hours and 55 minutes before might be 11 hours and 45 minutes or so. We're not sure. That's one of the main measurements, and that's the goal for the DART mission here. Now, DART is all about testing this technology, doing this for asteroid deflection, and importantly, doing this first test now before we need it. If there was an asteroid that was a threat to the Earth, what you'd want to do this technique would be many years in advance, decades in advance, such that you would just give this asteroid a small nudge, which would add up to a big change in its future position, and then the asteroid and the Earth wouldn't be on a collision course. And using this double asteroid system to develop this capability, take this first step to being able to deflect asteroids in the future, is really a smart and a safe way to do this first test.
Thank you so much, Nancy. We are moving on to Elena Adams, who is going to walk us through the road to getting to the asteroid.
Thank you, Karen. So we have been developing DART at the Johns Hopkins Applied Physics Laboratory, or APL for short, for about 5 years. And since we have a lot of partners all over the world, including the Italian Space Agency, who are providing us a small CubeSat that we're going to carry on top of our spacecraft that we're going to release about 10 days prior to hitting Dimorphous. So we've been in development for about 5 years. About a month ago, we went to our launch site at the Vandenberg Space Force Base, where we're going to stay for another 3 weeks, since this is launch minus 20-day briefing. We're going to stay there for another 3 weeks, completing our tests, getting ready to load parameters. We just loaded our propellant. And in 20 days, we're going to lift off on the SpaceX Falcon 9 rocket. One thing I want to say is that we're going to be launching, you might have heard 23rd or 24th. Well, the point is that we're launching on the 23rd in Pacific time, late in the day at 10:20 p.m. If we launch on our first day of the launch window, or on the 24th, which is Eastern time at 1:20 a.m. Most of the launches are late at night, as always, just for the press. So, so we're launching. Our launch period is actually pretty long for a planetary launch period. It's from the November 24th all the way to February 15th, so we could launch at any time during that time. We will spend 10 months on cruise, and we will get to Dimorphos right as Dimorphos is actually closest to Earth. So we could do the observations that Nancy just talked about using the ground-based telescopes. And we can also do other things, such as stream video back to Earth of our impact, and that's going to be pretty exciting. So over the 10 months, we're going to do a lot of different tests using our telescope called Draco, calibrate it, make sure that it all works. Also demonstrate some new technologies for NASA, such as the Next-C ion thruster, which is shown right here, glowing blue, and also the rollout solar arrays. As we said, about 10 days prior to arrival at Dimorphos, we're going to let go of the LiCheCube, and LiCheCube is going to follow us in. Now, about 4 hours in before we hit, we're going to turn on the smart Nav technology, and that is one of our new technologies that we're demonstrating for NASA. That's what actually allows us to guide ourselves into the asteroid, because we don't see Dimorphos at all until about an hour in. At which point, we will stop tracking Didimo, which is the larger asteroid, and we switch over to Dimorphos. And it becomes, it's just a little pixel on our camera, and the whole time the spacecraft does everything autonomously, it just follows in, and then we hit. And then that's it. That's DART, and then the telescopes come.
And then we make impact. So to tell us about that is Andy Chang. What happens when we actually get to the asteroid?
Yeah, thank you. The DART mission is about demonstrating deflection of an asteroid, changing its course, and doing it by hitting it with a spacecraft. So DART has to hit the spacecraft, the DART spacecraft has to hit the asteroid, then DART has to measure the amount of deflection, and then we want to understand why that deflection came about, how it works. So it's all about measuring the momentum transfer. How much momentum do we put into the asteroid by hitting it with the DART spacecraft? And if one day an asteroid is discovered on a collision course with Earth, then we have an idea of how big that asteroid is and how fast it's coming and when it will hit, that kind of information. Then we will have an idea how much momentum we need to make that asteroid miss the Earth. And so if you want to do that with a kinetic impactor, we also need to know how much momentum does a kinetic impactor put into an asteroid. So that's what DART will tell us for the DART impact. And to do that, we're going to be measuring, in addition to the telescopic measurements of the orbit period change of the Didimo system, we're going to be measuring with the cameras as we come into the target where we hit, what are the impact conditions, so what kind of terrain, is it sloping, are there boulders nearby, what kind of terrain we hit, and then finally we'll have LiTCube take pictures of the impact and to measure the impact ejecta. So LiTCube is released by DART. It's just a little guy, it's a briefcase-sized asteroid. It'll fly by Didymos on its own, and then it will turn around and will take pictures of the DART impact, of the ejecta. We need to do this because the DART impact at 15,000 miles per hour is going to blast tons of material, many tons of material off Dimorphos, maybe thousands of tons. And we need to know how much material there is, how fast it's going, and where it's headed. So with that information, together with the information from the DART cameras on where we hit and what the impact conditions were, that's what we'll use to determine the momentum transfer from the DART impact. So LiTCube is just such an exciting mission. It's the first deep space mission for the Italian Space Agency. What a way to start a program. It's unbelievable. I'm really excited. Thank you.
Thank you so much. And now we will switch to taking questions. We will be inviting the media to ask questions on the line, and we are also taking our social media questions with #AskNASA. So with that, I'm going to pass it over to our operator to tee up the first question.
Thank you. We'll now begin the question and answer session. If you'd like to ask a question, please press *1 on your phone and record your name at the prompt. To withdraw your question, you may press *2. Again, to ask a question, please press *1 and record your name. We'll take a moment for questions to come through. Please stand by.
And I will let you, operator, tee up the first one.
The first question comes from Gina Sinceri with ABC News. Your line is open.
Thank you. So tell me why you didn't pick an asteroid that would threaten Earth.
So I want to repeat that because it wasn't completely clear on our side. Was the question why you didn't pick an asteroid that was headed towards Earth?
Correct. That's the question. Thank you.
Great. I think that might be a Lindley question.
Sure, I'll take that. Well, we don't have an asteroid of that size, thankfully, headed toward Earth. This is a test. Nature has given us a setup where we have an asteroid, a binary asteroid that's approaching close to Earth so that we can observe from Earth-based observatories. But this is a test. We don't want to be in a situation where an asteroid is headed toward Earth and then have to be testing this kind of capability. We want to know about both how the spacecraft works and what the reaction will be by the asteroid to the impact before we ever get in a situation like that.
Thank you so much. We will go to the second question, please.
The next question comes from Dora Mendoza with USA Today. Your line is open.
Hello, can you hear me?
Yes, we can.
Okay, yeah. So you guys said that there's no real threat asteroid hitting Earth. So if there isn't, then why would you do this now? You guys instead do this once more in the foreseeable future.
Again, I'm going to repeat it and make sure we got it okay, which is that if there is no current threat to Earth, I believe the question was, why are we doing tests like this? Is that correct?
Yeah, and then if there's any plans to do this once more with any other asteroids.
Great, that one we could hear. Thank you so much. To Lindley again.
Yeah, well, although there isn't a currently known asteroid that's on a impact course with the Earth, we do know that there's a large population of near-Earth asteroids out there. In fact, we have over 27,000 near-Earth asteroids in our catalog now of all sizes. The key to planetary defense is finding them well before they are an impact threat, so we map out their orbits and where they're going and know where in time they could be an impact threat to the Earth. We can predict an impact threat to the Earth if we know about the asteroid and have tracked it decades in advance, or know the day that it could impact the Earth out into the future, as much as 100 years into the future. So that's really the key of planetary defense. And the question, are we going to test this on other asteroids? Yeah, well, we're going to plan to do future tests. But we might be testing other techniques. There are other ways to possibly deflect an asteroid. The principle with all of them is just to change the speed, the orbital speed of the asteroid, just a small amount, a nudge, as Nancy said, and changing that speed of the asteroid in its orbit, that changes its orbit. And so in the future, it won't be in the same place it was going to be, and to impact the Earth, it will be a mess.
Thank you. I'm going back to the operator for our next question, please.
Thank you. Our next question comes from Michael Greshko with National Geographic. Your line is open.
Hi, thanks so much for doing this. I think my question's for Andy and Nancy. Nancy, you mentioned that DART's goal is to alter the orbital period, of Dimorphos by about 10 minutes. What is the minimum change to Dimorphos' orbit that would be considered a success for DART? And what are the biggest sources of uncertainty that go into that estimate?
Start with Nancy.
Yeah, I can answer that one because we actually have that specific requirement. It is 73 seconds. So we are going to change it by at least 73 seconds. All the models show that it'll be much more than that. Some of the most uncertainty, and we know this from previous missions that have been to asteroids, is asteroids are complicated. They look different. They've got boulders, they've got rocky parts, they've got smooth parts, they've got weird shapes. All sorts of things are going on there. And so how exactly the DART spacecraft interacts with a real asteroid of this size and where it hits is one of the main factors for those models. And also how that asteroid's put together. We know a lot of asteroids are maybe like rubble piles. They're kind of things kind of put together. So how dense and how closely packed are these materials, or how distributed are they, can also really contribute. So it's really doing this real world test on a real asteroid is why we need to do DART.
Yeah, so a key parameter there is how strong the asteroid is. That will determine how much ejecta you produce, and also, so basically, what is the reaction to being hit by DART?
All right, we will take a social media question next, but I'm waiting to be able to see it, and then we will take a social media question. And we will take that in just a moment. So instead, we will go back to the media now. We'll get that question up shortly. For now, operator, I'm going back to you for the next question.
Thank you. Our next question comes from Paul Gross with WDIV. Your line is open.
Yeah, thanks very much for doing this. One thing you haven't discussed is in getting the spacecraft to the asteroid, we have a very special ion propulsion engine. Can somebody talk about why that's so special?
I'm sorry, I'm going to ask you to say it one more time. We're just having a little bit of a sound. One more time, please.
Sure. Can you talk more about the ion propulsion engine. Why is that so special? Because that's what's going to get the spacecraft to the asteroid, and I understand that's new technology.
Thank you. I think that is an Elena question.
Yeah, it is an Elena question. So the ion propulsion engine we're just demonstrating for NASA. It is not actually our means of propulsion to the asteroid. What we're going to do is we're going to use the typical hydrazine thrusters. They're 1 Newton thrusters. We have 12 of them scattered around the spacecraft. And we're going to use those to perform most of our trajectory correction maneuvers. The EP thruster, the electric propulsion thruster, we're going to turn on a couple of times during cruise, and we're going to just basically demonstrate that we can operate it in space, because part of the wonders of new technology is just that step from when you build it up to getting it to space and getting it to operate for the first time. So that's what we're demonstrating for NASA.
Thank you. We will have that social media question now. Jace Voracek from Twitter asks, what factors were in consideration when choosing Dimorphous as the target for the first DART mission, and were there other asteroids that were potential candidates? Maybe Nancy and then Lindley, if you want to weigh in too.
Or Andy.
I think it's Andy and me.
Oh,
yeah.
All right.
Okay, yeah. Okay. The Dimorphos and Didimos was always our best target. The reasons being it is a binary system, and it's such that this binary system is such that the two bodies are eclipsing, which means that they move in front of each other as seen from Earth. And that's what makes it very easy to measure the orbit period and also a small change in the orbit period that would be caused by the DART impact. And there are, we and also our collaborators in Europe, we spent years looking for other possible targets to do this mission, this type of a demonstration. Yeah, so the binary system, changing orbit period, and there really is not another good target anywhere near as good as Dimorphos and Didimos, because of how close it is, how readily observable, how long it's been observed also in the past, all these reasons. That's why Dimorphos, Didimos is the best target.
Yeah, and just to add to Andy's point, also the other thing we really considered is that this asteroid has to be fairly close to Earth at its point, so we can stream data back to Earth before we hit. And the other piece of the information that went in was that when we approach it, it has to be at such an angle that it gets lit by the sun, because we won't see, if the asteroid's really dark, we won't be able to see it and won't be able to hit using smart navigation.
Thank you. We're going to go back to our media questions now. So, operator, I'm tossing to you.
Thank you. The next question comes from Megan Bartels with Space.com. Your line is open.
Hi there. Thanks so much for taking my question. I have a couple of very short questions. One is the final mission price. One is whether the launch window is instantaneous or a certain period and how long. And then the other is if there are any post-launch milestones that we should be looking out for the actual arrival. Thank you.
Thank you. Can you repeat, please?
Well, I'll take the first question, the total mission price cost. The life cycle cost for this mission, DART mission, from the time it went into its formulation, concept development formulation, through the launch and launch vehicle, the almost year of operations, and then the following year of observations and analysis of the data, which won't end until 2023. The total life cycle cost is $330 million. You have to remind me of the second question.
Yeah, Megan.
I can grab those two.
Right.
Okay, sure.
Do you want them repeated, or?
No, so the second question, I believe, was, is it an instantaneous launch window? And the answer is yes. Every day we have one opportunity to launch. If we go in that second, we go. If we don't, we go next day at the same time. And we do that for up to 84 times if we really wanted to. I hope we go in the first one. And then I believe the second question is, are there other milestones we should look for after launch? And there are a couple of things. The first 30 days is the commissioning period. Then we're going to be firing up our Next-D engine about 20 days into it. So I think that that would be one of the milestones. We're going to open the Draco doors, which is our instrument. We're going to open the door and take first pictures about 8 days in. And then, of course, 30 days before we hit, we will see Didimos for the first time. So these are just the variety of milestones that we're going to experience along the way.
Thanks. We are ready for the next question.
Thank you. Our next question comes from Mike Porous with Aviation Week and Space Technology. Your line is open.
Thank you. You may have answered this, but I just wondered how long the observations post-impact will continue to give you the database you're looking for.
Andy, please.
Yeah, the observations will continue into the early spring of 2023, so February, March. This is the telescopic observations of the Didimo system.
Great, thank you. We can move on to the next question.
The next question comes from Marcia Smith with SpacePolicyOnline.com. Your line is open.
Thanks much. I was wondering, in the previous discussion, you were talking about how different asteroids are from each other, and of course, this is a very unique spacecraft. So when you're taking that measurement of momentum transfer, it seems to be like a very unique data point. And I'm wondering how extensible is going to be to the universe of asteroids. And is this one of the more common types of asteroids that might be headed towards Earth, or how much is this really going to help everybody deflect asteroids in the future? It seems like it's just one data point from one particular spacecraft versus one very unique asteroid.
Is that a Nancy question?
Yeah,
I think it might be. All right.
So what we do know about the Didymos-Dimorphos system is from spectral observations of telescopes of Didymos, and it actually is an asteroid type that is the most common type of asteroid out there in the near-Earth object population. It's like ordinary chondrite meteorites. We have samples that we've looked at here in the lab, and it's fine-grained mixtures of rock and metal together. It's actually 4.5 billion years old. It formed before the planets formed. It's like the leftovers of planets formation. So that actually makes this asteroid system a really good test in order to do this as well. Every asteroid is going to be a little different, just like rocks are a little different, but they share a lot of common characteristics as well. So when we do this test on this common type of asteroid, then it will be applicable to understanding these larger populations. And really, it's important to take this first step in order to do this first test so that we can develop capabilities going forward.
If I can add to that for just a second, the size of the moon, Dimorphous, 160 meters, and the smaller the asteroid is, the more frequently it could be a impact threat to the Earth. There's many more smaller ones out there than there are large ones. So testing against sets of small body is a challenge with the smart nav and hitting that small target that far away in space. So it's a good test from that standpoint as well.
All right, we will go on to the next question, please.
The next question comes from Devin Coldaway with TechCrunch. Your line is open.
Hi there. Thanks for taking the questions. I realize the data for this is meant to come out of this mission, but theoretically, is there some kind of Goldilocks zone for intercepting incoming asteroids where it's close enough we can be sure we can predict its motion and hit it far enough that the minimal impact we can make is enough to deflect it sufficiently?
Well, maybe I'll start, and maybe Andy will want to chime in. The right time to deflect an asteroid is as far away from the Earth as we can. As I mentioned earlier on, the strategy is to find these objects not only years but decades before they're any kind of an impact hazard to the Earth. So we have time to characterize them first, know where they're going to be headed, know what their size and composition is, and know what would be the most effective method to then change its orbit. But once we know that and have confirmed that it really is an impact threat, then is the time we want to take it, because the further away in space it is, years before the impact, the less force it takes to change the orbit enough that it will be a miss instead of a hit.
All right, we will move on to another social media question now. Rick Hubbard on Twitter asks, given that the gravity fields for Didymos and Dimorphous affect and are affected by each other's fields, what post-Dimorphous impact predictions are there, if any, for changes in the orbit for Didymos? Andy, please.
Yeah. Okay, so it is correct that Dimorphos and Didymos are gravitationally bound to each other, so they're orbiting each other, and so that when DART hits Dimorphos and changes its motion, there's also going to be a tug on Didimo. So the whole system will have its heliocentric orbit change, but only by a tiny amount. That's because Dimorphos is so tiny compared to Didymos. The change in the Didymos orbit, in fact, is, we've studied this and analyzed that. It's so small that, in fact, it could not be measured easily, and it is much less even than our knowledge of where Didymos is. The current knowledge of where Didymos is actually much coarser than the expected change, even under the most optimistic assumptions, the change in the Didymos orbit that would be caused by the DART impact. It's just too tiny to be measured, so it's a very safe experiment.
Thank you so much. We will move back to the media. So operator, I'm passing to you for the next question.
Thank you. The next question comes from Ramin Skiba with Wired Magazine. Your line is open.
Hi, thank you. I just wanted to ask, how did you, can you explain what angle DART will hit the moonlet at? Like, is it going to be parallel to its orbit, perpendicular, and why? Why do you want to select it in that particular direction?
Why don't we go to Elena?
You know, Elena.
So, it is a good question, but it is a funny question because we can't really predict the angle of impact onto Dimorphous that well. We know where, how we're going to hit in the trajectory, right? We're hitting it head on. And we know where the sun is going to be at the time. But the problem is that we cannot predict whether there's going to be a boulder or something. So our impact angle on the plane of Dimorphous is really uncertain right now, and it's really going to depend on what Dimorphous actually looks like, and we're not going to find that out until the last, well, let's be honest, last 20 seconds when we're about to hit. So we have done a lot of simulations on the ground, showing, looking at all different angles of impact to make sure that we can still transfer enough momentum into the body of Dimorphous and still are able to exact the change of at least 73 seconds. And the answer is that our lowest numbers come back something like 3 minutes. 3 to 10 minutes is a range. And we're looking across all the different angles. So.
And I guess I'll just add to that, too. We are purposely targeting the moon as it comes out from behind the other one to hit it as head-on as possible. And this is going to give you the biggest deflection, right? And it's about 17 degrees out of the orbital plane.
Out of the orbital plane, yep.
That it's coming in. So the local geometry, exactly like Lena was just saying, is, is going to be a big factor. And then we have to do this. But we are targeting to be as nearly head-on as possible to cause the biggest deflection in the system.
And nearly as center as possible as well.
As possible using smart nav. And
exactly.
It's going to be great.
Yeah, but it's going to depend on the lightning of the moon as well.
Yeah.
It's a good question. Thank you.
The other thing is also when you hit in that geometry, the two moons are separated by about as much as possible.
All right. Back to the media for our next question, please.
Thank you. As a reminder, if you'd like to ask a question, please press *1 and record your name when prompted. The next question comes from Morgan McFall-Johnson with Insider. Your line is open.
Hi, thanks so much. Can you just talk about the strategy once DART is over? How do you get to the point where you're prepared to effectively use this method on an actual hazardous asteroid? Do you need to follow up and do another test mission like this one eventually? And just as a follow-up, is this the kind of thing where you build a DART-like spacecraft and have it on standby? Or do you have to custom build a spacecraft once you discover a particular hazardous asteroid and how long do you think that would take? Thank you.
I'll pass to Lindley.
Yeah, I'll take that. Well, this test is to demonstrate that this technology is mature enough so that it would be ready if a actual asteroid impact threat was discovered. So after this mission, and we've analyzed it, assuming we don't have any major surprises, of course, we think that this technique would be then available, would be a part of the toolbox that we're starting to build of capabilities to deflect an asteroid. In studying all the different kinds of scenarios we could be faced with, the orbits of these bodies, the time that they could be discovered ahead of the impact, the velocities that they may have. We know that we need a toolbox of capabilities. No one technique, just kinetic impactor, may not be applicable in all the situations. So after we do this test for kinetic impactor, we'll want to do tests of other techniques like gravity tractor, for instance. Gravity tractor is you just station keep with a spacecraft off to the side of an asteroid, and nature's tug rope, gravity, will slowly pull that asteroid off the impending trajectory. Other techniques, ion beam, laser ablation, there are a number of good ideas out there that we would want to look into subsequent to DART. But the message is that our strategy is to have a toolbox of several different techniques after many years of testing different things. Luckily, asteroid impacts don't happen all that often, and so I think we have time to do these kinds of things. And we never know what the technology may be in the future when we are actually faced with an asteroid impact. We might have tractor beams and other types of technology that would be more appropriate at that time. This is just a start.
And Lindley, can I jump on
Sure.
and just say a couple of things also? Because DART is demonstrating some of the other technologies, things like the NEXI ion engine, for example, is a good way of getting to a variety of asteroids because you are providing a lot of really low thrust to the spacecraft. So you can actually maneuver around asteroids much more easily than you would with a traditional system where you're burning through a lot of propellant and you're using less propellant for that. So these are the type of things that we are actually demonstrating that might come in handy in getting to a variety of different asteroids, no matter where they are.
Thank you so much. We are going to go back to a social media question now. Nicole Choi from Twitter asks, how will DART find and hit the asteroid? Elena?
Good question. Thank you, Nicole. So we are going to be using optical navigation for a portion of the cruise where we used our telescope called Draco. And this telescope is going to be searching for Didimos the whole time. We are in space. We're really for real, starting about 40 days out before we impact. So right now we have a pretty good understanding of where Didimo's system is. And so when the spacecraft gets launched, the rocket puts it on a particular trajectory to go to Didimos. And in fact, if everything went well, if we're on a perfect trajectory, we wouldn't have to do any maneuvers at all. So we're going on our trajectory, and about 40 to 30 days out, we're going to start searching for Didimos, where we expect it to be. And the whole time, 40 days out to about 10 days out, we are taking images every 5 hours, and we're processing them on the ground here with the navigation team at JPL, who's actually processing images and making sure that we're navigating towards Didimos correctly. And we are still navigating to Didimos all the way in through 4 hours in, at which point the spacecraft starts navigating itself. And at that point, it's keeps navigating itself to Didimos until about an hour out, at which point it switches. It finds Dimorphous because, as Andy said, the moon will come out from behind Didimos. It finds Dimorphous, and then it navigates towards itself, Dimorphous. But the whole time is just based on the fact that we're taking pictures, and we know where it is.
We're going to go back to the media now. Operator, do we have the next question?
Yes, our next question comes from Paul Brinkman with UPI. Your line is open.
Hi, yeah, thank you very much. Can you hear me?
Yes, we can.
Great. One quick question about the impact timeline. The mission website says September 26th to October 1st. How does that change if the launch date is delayed? And then I also wanted to know, I guess there was going to be secondary observation by radio telescope, and Arecibo was part of that plan. Can you just explain what, if any, impact the collapse of Arecibo had on that plan? Thanks.
Thank you. Elena.
I'll take the first half of the question, and then I will throw it over to Nancy. Yeah. Yep. Sounds good. So the reason why it says September 26th through October 1st is it all depends on when we launch in the launch period. As I said earlier, we have 84 opportunities. If we launch on day one of our opportunity, we will hit Dimorphous on September 26th. And basically, as we go farther in a launch period, by February 15th, we're hitting it on October 1st. That constraint was really placed there just for the radar observations too, so that way the radar can actually see when Dimorphous is closest to Earth. So Lindley, over to you.
As we've said earlier, the real measurement of the change in the orbital period of Dimorphous about Didymos will be done with optical telescopes. It's done by observing the light curve brightness and dimming of this eclipsing binary when the moon goes in front and behind the primary object. So radar was never a prime requirement for the mission. That being said, it's always good to get radar observations because they provide very precise positioning. And if the signal is strong enough, actual imaging of at least the main body and maybe the position of the moon. A moon that small, that far away, over 6 million miles, is still hard to detect with our planetary radar. Yeah, we still grieve the loss of the Arecibo radar, but we still have Goldstone, the 70-meter Goldstone solar system radar capability, and we do plan to observe using Goldstone, and if the setup is right, we'll use the Goldstone to transmit, the 70-meter to transmit, and we'll receive the signal at the Green Bank Observatory in West Virginia. That setup, that bistatic radar setup, gives us the strongest signal-to-noise ratio and would provide the best observations in this particular situation.
And we'll take the next media question, please.
Thank you. As a reminder, if you'd like to ask a question, please press *1 and record your name. The next question comes from Michael Greshko with National Geographic. Your line is open.
Hi, thanks so much. Two quick questions. I think the first might be for Nancy and Andy. The second is for Lindley. There's been some questions about the long-term characterization of DART's effect. I was wondering if you could speak to how important the European Space Agency's upcoming Hera mission will be to understand the long-term impact of DART. And then for Lindley, you mentioned earlier the importance of detecting these asteroids as soon as possible. Earlier today, the Astro 2020 Decadal Survey was published, and it noted that satellite megaconstellations' biggest potential scientific impact on astronomy would come into play in the discovery of near-Earth objects. So I was wondering if you could speak to kind of the long-term plan for observing and detecting near-Earth objects and the potential effects of things like megaconstellations. Thanks.
Great. We will go to Andy for the first question and Lindley for the second.
Okay, so the European Hera mission will launch in 2024, and we'll visit Didimo's system in late 2026, and make very important contributions to understanding the outcome of the DART impact. So there's two main things it would do. The first is the spacecraft, the European spacecraft Hera, will directly measure the mass of Dimorphos. That's a measurement DART cannot make all by itself. We can make estimates, but there will be a direct measurement of the mass from Hera in rendezvous with the Didimo system. And the second important measurement they'll make is they'll be able to study the impact crater that the DART impact made. How big is it? How deep is it? And maybe even look for pieces of the DART spacecraft that may be left sticking out of the ground. Who knows?
Okay, well, the second part of that was what's going to be the impact of these mega constellations that are being talked about of 30,000, spacecraft, something like that, to these surveys, the ground-based surveys. The first thing is that, the current surveys, there are spacecraft up there now, satellites, debris, and it is something that we have to contend with our imagery from the ground already. But with that size of constellation, doing some estimating on some of our survey systems, the number of times that one of those spacecraft would be in the field of view when you've got that many up there, and just about every image that we would take would have one of those spacecraft in it. And so a part of the image, now these are very wide field images, so only a part of the image would be damaged, so to speak, by that satellite being in it, but it wouldn't completely disable the capability. But our real direction for the NEO program is our next mission that is under the formulation right now into preliminary design, and that is the Near-Earth Object Surveyor, which is a space-based IR infrared telescope that's being specifically designed to detect, track, and characterize near-Earth asteroids. It will be launched and positioned into space at the Earth-Sun L1 point, about 1 million miles sunward, and that'll be well away from Earth and won't be affected by these constellations. But it's still a area of concern because a lot of our characterization observations, and certainly a lot in the astrophysical realm, that still use the ground-based observatories, are concerned about the number of spacecraft that are up there and what effect they could have on the imaging from ground-based telescopes.
Thank you so much. We are going to take another social media question now. Steve from Facebook asks, what is SmartNav and how does it work? I think that's for Elena.
Thank you, Steve. All right, so SmartNav is a set of algorithms that we use in order to be able to find and hit Dimorphous. And these algorithms come from the development for many years at the Applied Physics Laboratory for missile defense, where they also look for really small things and they try to hit them. But in this case, we're using it for planetary defense. And it's a set of algorithms that control our thrusters, which are a main way to propel our spacecraft. They control our attitude to make sure that we can actually point our imager at the asteroid. So we're pointing our imager at Dimorphous, we're taking pictures, and those pictures add up in the spacecraft, and they're processed to see if we can form a track to that asteroid. We basically are taking out the attitude motion of the spacecraft, and we're trying to see if we can keep tracking that one dot that we think is the asteroid. And that's how it basically works. At some point, it switches over to Dimorphous from Didimos, and does the same thing the whole time. It's trying to correct its attitude and correct its trajectory. So it centers itself in space and figures out, where am I? Where do I need to go in order to be able to have, to really directly hit this dot?
Yeah, the main thing, it has to take into account orbital motion too,
Yes,
in addition to just linear flight.
That's right. That's right. The fact that the Dimorphous is not just going back and forth, and you're seeing a 2D image of it,
right.
That adds up as well. As well as stars popping in and out of the field of view of the star tracker.
Yeah.
It's a little bit more complicated, but that's the basics.
Well, thank you so much. We will go back to a media question now, please.
Thank you. The next question comes from Megan Bartels with Space.com. Your line is open.
Thanks so much. This might be sort of a basic orbital thing, but could you explain why if you hit Didimo head on, it will speed up the orbit instead of slow it down? Thanks.
All right, we'll pass to Andy for that one.
Okay. Yes, when we hit Dimorphos head on, instantaneously you are slowing down the moon in its orbit. But because it's slowing down, what happens is that the centrifugal force that's holding the moon away from Didimo's gravity, the centrifugal force is reduced, and so the moon falls closer to Didimos. When it falls in closer, it speeds up. This is the same process as the skater who's turning, pulling in her arms, and she spins up faster. It conserves the angular momentum. So the same process, Dimorphos coming in, swinging in closer to the main body, it has to speed up to conserve angular momentum. Of course, when it goes back out again in its orbit, it slows down again. But the speeding up is more than the slowing down, and on the average, the orbit period is shortened, and on the average, the orbit speed increases. So that's what happens. Even though we hit it head on and instantaneously slow down the target.
Thank you. The next media question, please.
Next question comes from Marcia Smith with SpacePolicyOnline.com. Your line is open.
Thanks so much for letting me ask a second question. Someone brought up earlier about how the astrophysics decadal survey is out today, and it makes me wonder about the planetary science decadal that's underway. Are they evaluating planetary defense missions and how you should prioritize the type of techniques that you have, apart from kinetic impact, and to help you prioritize where you should be investing your money for future missions? And if that's not part of the decadal, is there some other group within the academies or somewhere else that helps you prioritize whether to invest in these kinds of missions or invest in, is it NEO-SM, the survey mission, or ground-based identification of asteroids? How do you sort all that out? Who is it that advises you?
Well, we happen to have the perfect person to answer that question here, and that is Nancy.
That's not the intro that I was expecting there, Lindley. I'm serving as the chair of the Small Bodies Panel for the Planetary Decadal Survey that's currently ongoing. We've had a number of open sessions, and you can check out the website for there. But yeah, planetary defense is within the scope of the Planetary Decadal Survey for the first time. So this next Planetary Decadal Survey that comes out will include a discussion of planetary defense and priorities looking forward for the next decade. Obviously, that's not scheduled to come out until next March, so I really don't have a whole lot more to say about that. But if you want to add on to that, Lindley, I think it's really great that planetary defense is being included in the decadal survey for this time.
Yeah, it is, and it signifies that the planetary defense program is an important part of the overall planetary science portfolio at NASA now.
We do have one last social media question. I think if we answer it quickly, we can fit it in before we have to go. Sharon on Twitter asks, do we already know what kind of surface Dimorphous has? And if it turns out to be a porous surface, would the redirection still be effective?
Okay, do we already know what kind of surface Dimorphous has? The answer is no. Simple as that. We know nothing about it. It's just barely resolved, even in the radar data. And will the redirection still be effective? Yes, we believe so. The amount of deflection we get is uncertain. Porosity affects that, but there will be a redirection. We are confident of that.
Thank you so much. Thank you to all of our speakers for being here today. Thank you so much for joining us. Keep watching nasa.gov/live for that launch coming up later this month. And in the meantime, thank you. Goodbye.
Thank you.